Okay, this is continuing with the complex numbers lessons. This is, so you watch the polar coordinate video, and you understand the idea of getting to a point by first moving on the polar axis and then a rotation. And this is the connection of the Argand diagram. Now, if you think about it, we can so once again, so this is 16b Argand diagram. If we can refer to complex numbers as a vector, any x, y, that's the idea, whether it's, in the real plane, this is x, y. So this is vector x, y, move 3 to the right, x to the right, y up. But we saw last year that this could also be the Argand plane. You saw last year the Argand diagram, which takes the complex number x plus iy. It takes the components technically like a vector. And so, yes, this is the real axis, and this is the imaginary axis. And so if you have x plus iy, we said, you know what, let's view that as like a vector with an x component and a y component. And we can graph the same idea. Here's x plus iy. And once again, that was from last year. So that's the connection between vectors and complex numbers. Complex numbers are vectors. All numbers have this geometry. Okay. So let's talk about, once again, it's kind of a review. You actually did this with vectors, but we can do this again. The idea is you want to be able to go from a complex number and represent it as using polar coordinates. Take the x, y, and turn it into a modulus. This was the modulus. If we said that z equal this, and we use that notation, like the absolute value, it's the distance from the origin to the point. Distance from origin to the point, to z. And this is our argument. And we saw it's like the rotation. So, we went out on the polar axis and we did a rotation until we got to the point. This gives us a geometry of numbers. This gives us a distance and a rotation. It's kind of interesting. So, yeah, okay. So how do we go from representing as the xy to the modulus and an argument? Well, we can just draw a diagram here. So we knew that we have this point here. Let's call this x. Because it's complex numbers, let's call it x plus iy, right? And so, this is, and so this was x, and, this is our y. And the idea was, we saw the visual here. Here's our visual, right? So we know, and so the idea is, yeah. And then we saw this is, this is our r, and this is our theta, right? Because once again, this r and this r are both radii of the same circle. So first of all, what do we want to do? We want to take our xy. We want to take our xy and go to polar coordinates. So let's think about this. Well, this is a Pythagoras theorem, right? So we know that x squared plus y squared equals r squared, and therefore r, which is the modulus of z, is equal to the square root of x squared plus y squared. Now, how do we get to the theta? Is there a relationship? We can say, okay, fine. The tangent of, if we have our xy, the tangent of y over x is, the tangent of theta is equal to y over x. So theta is equal to the inverse tangent of y over x. So with your x and y, you can get to your modulus and you can get to your argument. With regard to the argument, you have to kind of visually know what the area is because your calculator is going to give you some reference angle. It's going to give out you a positive angle or a negative angle, but you need to still determine like exactly where it is. If it's in the first, the second, the third, or the fourth quadrant, you can visually see that where it's going to be. The next thing is, can I go from theta? If I have a modulus and a theta, how do I go to back to like my Cartesian, my x and my y? And that's simple. Also, we see that. So let's start with cosine. We know that the cosine of theta, you can visually see it here from SOHCAHTOA, is adjacent over hypotenuse, and therefore x is equal to r cosine theta. And once again, the second relationship is the sine of theta is equal to the opposite over the hypotenuse, or y over r. And so the y coordinate can be found by combining r and the sine of the argument. And these are just exercises going back and forth, right? So, for example, if I tell you 2 plus 3i, like 2 plus 3i. So we know the location, but now I want to represent this as a distance from the origin and a rotation around. So the distance, the modulus, that's easy. That's the square root of 2 squared plus 3 squared. Can you see over there? Oh, I'm about to lose you. That is the square root of 13. And then to find the argument, we know it's the arctan, or the inverse tangent. I keep mixing those two, but I really shouldn't. Let's just say the inverse tan of 3 over 2. And we can ask our calculator. Let me get my calculator from my bag. So you turn your calculator on. You go to trig, inverse tangent, enter 1.5, and I get 0.982. That's 0.2, let's see. So that's about 0.982 radians. How do I convert that to degrees? Well, I just multiply that by 180, and then divide by pi, and I get 56 degrees. About 56 degrees. We could try another one. How about 7 minus I? Let's see, where's my eraser? Right here. I'm erasing. 7 minus I, so let's see, am I over there? Perfect. 7 minus, well, I can visually see that my modulus is radical 50, and my argument is the inverse tangent of negative 1 over 7. Now, let's see what the calculator tells me. So let's do that. Let's do a trig, inverse tangent of negative 1 divided by 7, enter. It gives me negative 1.4. Let's multiply that by 180. And divide that by pi, because I'm really bad at speaking the language of radians. And I have like negative 8.1 degrees. So it tells me it's negative 8.1 degrees, right? But where is that? Is that the right answer? Well, I'm looking at my picture, right? Let's see, 7, negative 1, so it's here. So you can either write, I'm assuming you recall this a little bit from last week, you can write this as radical 50 cis, negative 813, or if you wanted to use from 0 to 2 pi, 360, you would write 50 degrees cis, 311 and 87 degrees. So either you can represent it this way or this way. It's up to you, it doesn't matter. But the idea is that you know that it's in the fourth quadrant and not the second quadrant, because you can visually see 7 minus I is in the fourth quadrant. Now, obviously, you can just plug these numbers into the formula. You can make the quick triangle, but I want you to start thinking. I don't want you to keep plugging it in. I want you to kind of have a sense, because from trigonometry. So for example, if I just give you the number 3i, I don't want you plugging it in the formula. I want you to say, you know what? Wait a minute. I know where 3i. It's right there. And I know how to get there. I know go out 3 and a rotation of 90. Once you go out 3 and a rotation of 90 degrees. Immediately, you know this as 3 cis 90. Just like that. Let's take the number negative 1 plus I. You look at that and you're like, wait a minute, I know that. You can see where it is. Negative 1 plus I, it's over here. Just by inspection, you're like, wait a minute. I can see that the modulus is radical 2, and I just know this is on the line y equals negative x. So I know it's over here. I know that's 135. Just by looking at it, I know. And that's totally fine. So you know this is radical 2 cis 135. That's what I'm going to practice. Most of these things that you can do quickly, and it's totally fine to do that, are the special angles, 30, 45, 60, 120, 135, 150, 225, ... Also, you might find numbers right on the axis. What's the next thing I'm going to ask? Negative 7. How do we represent negative 7 as an argument, a modulus and an argument? Well, you just visually see, wait a minute, this is negative 7. How do you get there? Okay, that's easy. You go out 7 on the polar axis, and then you just do a rotation of 180. So negative 7 is now 7 cis 180. And that's it. So when you're redoing 15b, yeah, you're going to do back and forth, but you're just going to immediately recognize, what these values are. And a lot of them are the special angles. You wonder, why aren't they letting me use a calculator? And you just have to say, oh, you know what? I know these. I know where these are. And that's basically it. Okay.